Good afternoon. Assalamualaikum warahmatullahi wabarakatuh. Uh, Today we're going to be presenting our machine learning project about analyzing stunting cases in Indonesian provinces and creating a stunting prediction model. Um, I'm Muhammad Fazil Maulana, and I'm with my friends here, Melvin Cahyadi Tirtayasa and Ashkafi Malasaid. Okay, so let's begin. So during our first presentation of our project in class, we introduced the dataset that we were planning to use for the project. This dataset was sourced from a local medical center in Yogyakarta. However, the dataset had only around 750 data entries, and the features of the dataset made it difficult to perform effective clustering algorithms. As shown in this, as shown in these figures, different clustering techniques didn't yield comprehensive results. The k-means clustering simply partitioned the dataset, and the dbScan algorithm didn't cluster the data properly. To resolve this problem, we started to search for more complete datasets with features that can be more easily manipulated in order to produce better results. After searching through public datasets in Kaggle, we found two particularly interesting datasets. The first dataset is about the prevalence of stunting in different provinces of Indonesia. The second is obtained from another public Kaggle notebook. This dataset contains about 120,000 records detailing the information on age, gender, height, and nutritional status of toddlers from around the world.
Now that we have two data sets about stunting, we can perform a more thorough technical analysis of the data. First, we cluster the percentages of stunting in Indonesian provinces using the three aforementioned clustering algorithms. We're using k-means, we're using dbScan, and we're using hierarchical. For this, we can look at the data year by year and compare the years accordingly to find trends in the data. In the first data set, we had data about years 2020, 2021, 2022, and 2023. All right, so first, we will apply k-means clustering. We have to determine how many clusters the algorithm will create from our data. So to find it, we will use the elbow method. Once we have found the optimum number of clusters, which we found was 3, we must then perform a standard scalar transform to our data frame so that the model will have a better time understanding the numerical data in our data frame. Once we have found the optimum number of clusters, which in our case was 3, we can apply k-means clustering on the data. We also should scale the data. By applying the algorithm to different years, we can find and compare trends and find the difference between clustering algorithms. By applying k-means clustering to the data from the year 2020 and 2023 for all the provinces, we get these two figures. We can see that the orange cluster, cluster 2, and the orange cluster, cluster 2, in 2020 and 2023, the amount of members in the clusters decreased by 1. This shows a decreasing trend in the amount or percentage of stunting or stunted toddlers in Indonesia as well. The next slide I'll give to Fazil.
Right. So yeah, we discussed the k-means algorithm before, and now let's move on to the dbScan clustering algorithm. So the dbScan clustering algorithm allows us to choose a variable called EPS. This value greatly determines the result of the clustering. And in order to find the optimum epsilon value, we use a method called k-distance graphing. For this k-distance graphing, essentially we use it to determine what's the best epsilon value. And to do this, we see which part of the graph has the most steepest curvature. And as we can see here, the steepest part is at around 0.1 or 0.15-ish. Once we have found the optimum epsilon value, as well as scale the data, we can apply the dbScan clustering algorithm on the data. By applying the algorithm to the data on different years, we can find and compare again the different trends between the clustering algorithms. Here we can apply it to the same years, 2020 and 2023, like we did in k-means. However, we can see that the result of the dbScan clustering for 2020, the year 2020, shows 5 clusters instead of the one from k-means, which showed 3. However, the 5 clusters began to somewhat dissipate in the year 2023, which as we can see, there are only 3 clusters. We think that this is the reason for this is that when we were applying the k-distance graph, the graph was slightly different for the year 2020. Here in the PPT, the distance graph, k-distance graph, is for the year 2023, which shows a very clear curvature in the k-distance graph, meaning that it's very easy for us to locate where is the optimum epsilon value, as there's a clear steep jump in this part of the graph. In our report, we showed the k-distance graph of the year 2020, and the graph was very jagged, as in there's a lot of jumps in the graph. So it was not very clear for us to choose what is the correct epsilon value. For both of these graphs in this slide, the epsilon value was 0.15. So yeah. So let's move on to hierarchical clustering. So in hierarchical clustering, the method is quite similar to the k-means clustering algorithm, in which we also use the elbow method to determine how many clusters we will have in the final result. And since we are using the same data set for the same year, we can just use the old result of the elbow method, which is 3 for the number of clusters. So it's the same for the hierarchical and k-means clustering. So once we found the optimum number of clusters as well as scale the data, we can apply the algorithm on the data. And by applying the hierarchical algorithm on different years, we can find and compare trends between the different clustering algorithms. Applying it to 2020 and 2023, we get the following result. So just visually from looking at the 2 graphs, we see that the way that the hierarchical algorithm works differently compared to the k-means. Mainly, the algorithm doesn't shuffle the x-axis of the graph. As a result of that, the clustering doesn't really get, I guess, compacted into more distinguished clusters. The clusters itself is just colored into their specific cluster color and not shuffled around compared to the previous clusters here. We see that the x-axis for the provinces are moved around in order to accommodate, or not accommodate, but adapt to the clustering result. And yeah, for The uh, I guess conclusion of the hierarchical clustering is that it's not really effective in showing any distinct trend in the data. Well, I guess you can mention that the cluster one for 2020 has greatly reduced number of points compared to the one in 2023, indicating that there is a downward trend in the stunting percentage in the provinces. With hierarchical clustering, there is a feature, or not a feature, but a characteristic for the clustering algorithm, which the hierarchy of the clustering can be visualized using a dendrogram. Um, because the data itself isn't uh that different, we see that for 2020 and 2023, the shape of the dendrogram isn't that different. Mainly we can see the difference in the orange cluster here. As we can see in 2020, there's more steps in the hierarchy because there are more data sets or data points in the first cluster. Yeah, as opposed to 2023, there's not many steps in the orange cluster because in cluster one, there's only 1, 2, 3, 4, 5 data points. Right, so we're going to move on to classifying, and I will let my friend Melvin continue from this slide.
Okay. For the classification part of our project, we have decided to use the decision tree classification for a couple of reasons. First, the second dataset contains a vast amount of data, 120,000 data points. And two, uh, as a class, we have only covered the material about decision tree classification. So we will only use decision tree classifier. Here, in the second dataset, we have a dataset with 120,000 uh, rows. And for the columns, we have the age of the toddlers, the gender or sex of the toddlers, and the height of the toddlers, as well as their stunting status or their nutrition status. Here we can see the properties of the dataset. We can see that um, we can see the distribution of stunted sorted by age. We can see the distribution of normal toddlers sorted by age, and also for severely stunted, and also for tall toddlers. So for the second data set, we also need to pre-process the data. We apply one hot encoding to the gender or sex column to identify true for either male or female. And we also apply data scaling to the age and the height of the toddlers. So for the second data set, we apply decision tree classification algorithm. With this, we can identify the stunting in children by having data on their height, gender, and age. From the model we created, we are able to gain an accuracy score of 99.9%. This is because of the robust decision tree created, which is able to pretty accurately identify stunting based on those metrics.
As a conclusion, from our clustering algorithm, we can conclude that there is a downward trend in the amount of stunting in Indonesia, visible by the decreasing amount of provinces in the clusters of high stunting percentage. We can also conclude that different clustering algorithms yield somewhat similar results in that they have grouped data based on how close the data points are to one another, yet they differ in how the clusters are created, as in the number of clusters in some cases are different and the overall shape of the clustering is also different. As for the classification, we have developed a very accurate and precise classification model using this decision tree of stunting cases, using decision tree of stunting cases in children. This can be demonstrated by inputting values of height, age, and gender back into the algorithm and then it outputting a suitable status for nutrition. I would like to demonstrate um, the working of the algorithm. I would like to demonstrate the accuracy of the model. As you can see, we have chosen these values. These values are negative because we need to input a number that's suitable to the encoded numbers in our data frame. And we can see these numbers are selected from the table up here, which is these two numbers. And the gender of the second entry is indeed male. And it should output the status of tall, as well as, status of tall, which is tinggi in Indonesian. And if we run it, we do yield as a tall value. Now we can try adjusting this number. So the left number is the age. So let's say we increase the age by some arbitrary amount like 0.4. However, oh, sorry, should be increasing, that means in the other direction. So 0.0. And then let's also increase this value of height. Oh, sorry, let's increase it, but not by too much. So let's do 0.7. We run it. We can see that it is severely stunted, which makes sense because with increasing age, the height must also increase accordingly. Now let's try increasing the height just a little bit more, 0.70. Still severely stunted. Let's try increasing it again. Still severely stunted. Normal. Ah, see, it's normal up to this point. All right, cut.
All right.
Go back here. Okay, count me down.
3, 2, 1, action.
So after that demonstration, we would like to conclude our presentation. And we understand that this might not be the smoothest presentation as it is it is quite difficult for us to smoothly do it all in one take. However, there is a much more detailed explanation and analysis in our report that came with our submission of the project. And we also linked the Google Colab for a more in-depth look into our code. There are also some notes and comments in the code so that, in order for the reader to be more, in order for the reader to understand it better. But yeah, I think that will be all from our group. Thank you very much for listening and very much for listening. That will be all from us. Assalamualaikum warahmatullahi wabarakatuh.